that this is an example of a systematic code because it contains an identity submatrix. Okay, so from now on we'll only deal with systematic linear block codes because they are easier to specify the parity check matrix, which I'll address in a second. But first I want to point out the following. Note that the sum of any two code words is also a code word. In other words, if I have, let C be the set of all valid code words, then we have if C1 and C2 are both in the code, then C1 plus C2 mod 2 is in the code. To show that, there exists M1 such that M1G is equal to C1. So in other words, there's some message corresponding to C1, and there exists some M2 such that M2G is equal to C2. So in other words, both these messages, both these code words arise from some message that's multiplied by the generator matrix. So therefore, C1 plus C2 is equal to M1G plus M2G, which is equal to M1 plus M2G, which is equal to M prime G. So there's some message that is the sum of M1 plus M2 mod 2, which is M prime G, which is equal to C1 plus C2. So in other words, there's some valid message that corresponds to the sum decode word C1 plus C2. As another note, that every linear block code contains the all zero code word. How do we prove that? So if every code word is,
if the message is all zeros.
MG exactly. If M is all zeros, the all zero message must be the all zero output. So that corresponds to all zero message. So in fact, that's consistent with this, and in fact, it's necessary that this be true in order for that to be true, because I can add to any code word, the all zero code word, which results in itself, and therefore C1 plus C2, so if C1 is some code word, C2 is the all zero code word, it must be true that the sum of those is also, it is just C1, so therefore that's in C. Okay, Let's talk about the parity check matrix. So we've got two matrices here, the generator and the parity check. We know how to encode a message. Now the question is, how do we decode the message? And that's where the parity check matrix come in. So the parity check matrix has the property that G times H transpose is equal to a zero matrix with dimension, this is K by N. H transpose is now N by N minus K, so this is then K by N minus K. What this means is that for any valid code word, it must be true that C times H transpose is 0, where this is the 0 vector, 1 by N minus K. How can we prove that? So C,
there's a G in C.
yeah, that's right, there's a G in C, so C is equal to mg. So therefore, CH transpose is equal to mgh transpose, which is equal to m times the 0 matrix, which is equal to the 0 vector. So, this is why I said a second ago that a linear block code may be thought of as a subspace of a vector space. So for any subspace, a linear subspace is closed under addition of any of the vectors. So we have that here. So for instance, think of a linear subspace of a three-dimensional vector space. A linear subspace is a plane. So any vector in that plane, passing, as long as that plane passes through the origin, it's a valid subspace. Any vector in that plane, if you add two of them together, they're still in the plane. On the other hand, there exists a dual to that space, which is orthogonal. So in fact, there's a one-dimensional dual to that space that's orthogonal to the plane. Here we have the same idea. So we have a matrix specifying our subspace, G, where any two code words in that subspace added together will also be in the space. H may be thought of as the dual to that space. So if I multiply any code word by basically what this is the basis for the dual space. If I multiply by the basis for the dual space, it's basically orthogonal to that space, because the dot product between C and all the basis vectors are 0. That's one reason why there are exactly k rows here and exactly n minus k rows here. So these matrices are both of full rank, and there are a total of n possible dimensions, which must be split up between G and H. So G is the space, and H is the dual space to that. So therefore, all of these vectors must be completely orthogonal to the dual space. And our test for whether or not something is a proper code word or not is if, when I take its dot product with the dual space, the result is 0. In other words, it's completely orthogonal.